Oké, dank je Dirk. Komt het knopje even.
Graag gedaan.
For the people at home, I said that current clinical issues starts November 2nd, and I will open the Canvas webpage next week, so you can see the schedule and so on, the study materials. But today, this is the schedule. So we're going to talk about first now, what do we want to do? Well, what do I want to do? So this is basically my research that I'm going to talk about next 2 hours. And a few years ago, in the meantime, maybe already 10 years ago, I came into contact with the neurosurgeons here at the VU Medical Center. And when they operate on a brain tumor, they have oh, that's strange. They have, it should be in front, of course. Normally it's in front of the other image. So before the surgery, they make an MRI image of the brain, of course. And fortunately, you just see here still this whitish area. That is the brain tumor. And most tumors are gliomas. And this is a diffuse growing tumors. Already the edge between healthy tissue and tumor tissue is difficult to say. But while the surgeon operates, he has to decide on visible information or tactile information on what is tumor or not. So in the end, he says a little bit yellow, a little bit pink, let's cut. And a colleague of mine who was present during these surgeries, and then after surgery, of course, the material goes to the pathology lab. And then the excised material is fixated and stained and sliced. And then it can be inspected to see what the nature was of the excised tissue. So a colleague of mine was present at one of these surgeries, and he knew about our work on this third harmonic generation microscopy. So he said, yeah, anything you can do to make this better will be important. And so if you want to be meaningful here, what we need to look deep in the life, deep into the tissue. Sorry, I'm a bit, I thought something else was following here. And so what limits us from going deep into tissue with microscopic resolution? Well, if you, okay, you didn't see that. I'm a bit messed up today. But so if you have light, so we want to look with light, and we want to look into tissue with microscopic resolution. So what kind of processes happen when we focus this laser beam on the tissue? So I'm sure Dirk has talked to you about the processes that happen into tissue. So what kind of physical processes happen? Can you name a few? Absorption, yeah. Reflection, yeah, that's a good one. Maybe another. And just in the tissue, the light will scatter, right? So as summarized here, you mentioned reflection. We don't go into the tissue is scattered, and part of the tissue will be absorbed. And then either this absorbed energy will be transformed into heat, or absorbed light will be emitted in the form of a photon again, usually of lower energy, and then you have fluorescence. And well, scattering is wavelength dependent, and it also depends on the particles, on the nature of the tissue that you have under your microscope. And in here are two examples of skin and breast tissue, and you see that the scattering coefficient goes up the shorter the wavelength is. And also absorption is wavelength dependent. And what I show you here is the absorption spectrum of water, because your body is actually full of water. So it's a very important component to consider here. And you see here on the x-axis we have wavelength, the y-axis we have the absorption coefficient. And well, maybe you know already, but I always ask here, and because you see here the visible part of the absorption spectrum, and this is the full, this is a large part of the electromagnetic spectrum. Only this part we see with our eyes. And so why do you think that nature, our eyes, have evolved sensors that are sensitive only in this small part of the spectrum? Why don't we have eyes that are sensitive here or there? And the answer is, of course, in this graph. Sorry?
Because you can see the colors.
No, but that is the sensors. So they're colors because you are sensitive. You have these rhodopsin molecules, proteins, which are sensitive to blue light, red light, right? And then we call that blue. But why don't we have eyes that say, oh, I can detect 100 nanometers, and I call that blue, right? It's a matter of where these sensors are sensitive. Now, the answer is in this graph, yeah?
For eyes need to have more, but yeah, I think it's somewhere in there because that's the only part where it's not super low.
Actually, you're the first one in years to give this.
Oh, really?
Yeah, it's such an easy question, right? That's why I keep it in. Indeed. So what you see here is the water window. Yeah? The water window here is where the water has a very low absorption coefficient. And if your eye would be sensitive there or there, where there's the water absorption is high, I mean, you would be sensitive only, you could see only for a distance of this, or maybe even less, because even your eyeballs are filled with fluid, right? And this absorption coefficient is per wave number. So it's the how much you go down per centimeter of path length. So yeah, and also the air is filled with water vapor, of course. So yeah, congratulations, you're the first in years to, and I also think it's such an obvious, because the answer is there in the graph. Okay, now nobody will forget anymore. Okay, but it also means that we have to, when we want to look deep in this live tissue or excised tissue, we need to take that into account, this water window, right? And it's not only water that absorbs, of course. So this is again an absorption coefficient. And so here is the water absorption. Now I write the absorption coefficient, and in the other graph it was the attenuation coefficient. So this the y-axis is converted. So now low absorption, low y-axis is better. So the absorption of water goes down at shorter wavelengths, but you have other components in the body which start to absorb. So collagen a little bit, hemoglobin absorbs, fat absorbs. So blood is red, fat is yellow. All are the components in the body that absorb light. And you want to be in a region where this absorption is low. So here, basically, now if you consider this, this optical window is between 600 and 1300 nanometers. But you also have the process of scattering, we just discussed. And here I plot the attenuation length again. So here you want to have a high attenuation length, so a long distance before you get a scatter event. And then you see that it is better to use, to use a shorter wavelength. Wow, this was a programmed transition or something. But if you take the two into account, so both the absorption, only water and scattering, you see that there's in this region between 900 and 1600 nanometers, it's pretty constant, the effect. So this is just to show that indeed, so both the penetration depth, because of these processes, the scattering, the absorption, the penetration depth of light into tissue is wavelength dependent. Just a nice picture I found, so to summarize my message. And this, I hope you can read it from the back of the room, but can you read it or not? Okay, otherwise you would have to move. But it's a simple solution here. Different optical techniques. So MRI, it's of course a very useful technique. Can image the entire body, but the resolution is not so good. It's only a millimeter or so. And if we want to go to higher resolution techniques, because we want to see more detail of the cells, to know what kind of tumor it is, for example. Then the higher the resolution, the less penetration depth you can achieve. And so we have here optical coherence tomography, I guess, for ultrasound, photoacoustic imaging, OCT, I guess you heard about that already. And today we're going to talk about the confocal or nonlinear microscopy techniques. This is because I contributed to a talk of a laser company, and I thought they sent me their presentation, so I stole again some of their sheets. That's why it talks there about the costs of this laser apparatus. So microscopy then is what we need to get this high resolution, to get the cellular resolution. And well, the microscope depends, of course, on the on lenses, the microscope objective. And just because I guess you've had that already in your optics courses, just very briefly, if you have a lens, the resolution is determined by the NA of this lens, the numerical aperture. And the numerical aperture is given by the dimensions of the diameter of the lens and how tight it focuses. So if it focuses very tightly, this F is small and you have a large NA. And it is determined by the wavelength of the light. So, for example, if you use light of 400 nanometers and a large NA is already 1, then you can achieve a resolution of about 200 nanometers. And because what we do is multiphoton microscopy or non-linear microscopy, so two terms for the same thing. And here the comparison between the two. In the next slide, I will explain it in terms of energy level diagrams. But if you have a regular linear confocal microscope, and you focus your beam of light to a small dot, because that's the resolution you want to achieve, then if you have in the sample, it is filled with fluorescent chromophores, and your signal is generated all over this cone that is pink here. And but you still want to select only photons that have indeed passed through this pinhole. So what you do in confocal microscopy, and because they're scattered, so to image this focus onto your detector and to reject all the photons which have scattered a bit, so the blue photons photos here. What you do is you place a pinhole before the detector to select only those photos. And effectively what you do then is you throw away a lot of your signals. So what we do in two-photon microscopy is that we use two photons to excite a chromophore. And to do that, two photons of half the energy, so they match the same energy as here. But these two photons need to be of the same on the same place on the same time. So here the photon density is not high enough, but in the focus it is. So you know that all the signal that is being generated by definition comes only from the focus. And here then in this setup, you can just open up your detector completely, because by definition all the signal photons come from the focus, and the detection efficiency is larger. And this is now the explanation in terms of energy level diagrams. So what you do if you have a cuvette or a sample with fluorescent chromophores, you excite a chromophore from the ground state to the excited state, and there you get some relaxation processes, and then you get your fluorescent photon, which you can detect. And so, and if you now, these chromophores usually you apply selectively in your sample, so you can image certain structures. Yep. Chromophore, yeah. Kleurstof, dye. Yeah. Label, fluorescent label. Yeah. Fluorescent label is but it is a molecule that absorbs light, and that's why I call it a chromophore. And so for your experiment, you have labeled, for example, specific cells with a fluorescent label, a chromophore. And what happens then is the chromophore absorbs light. It goes from the ground state to the excited state. You get some relaxation here, and then you get this green photon out, which you can detect. But for the two photon processes, what you present is two photons with each have half the energy, and but together they match also this total energy difference. So you also here you promote this chromophore from the ground state to the excited state, and you get the fluorescent photon out. But now the so these photons have half the energy. So they have a 2 times longer wavelength, right? Because energy is, of course, the energy of a photon is given by Planck's constant times the speed of light divided by the wavelength. And so the advantage, one of the main reasons, one of the reasons to do 2-photon or 3-photon microscopy is because you have then the signal is only generated in the focus. So you have this intrinsic confocality, what I sometimes call. And you have just this point, which you can scan in 2 directions. You can image a plane, but you can also go deeper in the tissue, and then you have a 3D. You can make a 3D image of your sample. And the other important advantage is that because you use here a longer wavelength photon, the scatter is less, and you penetrate deeper into the tissue. So that relates to what I was saying. So you want to work in this long wavelength region between, let's say, 700 and 1300 nanometers. Because then the penetration in the tissue is deeper. And this is how you realize that. First. So what we do is we scan our laser beam over this lens. We record the intensity, and then we make a map of this intensity versus position. and you get your high resolution image. And what I said in this, I said here in the previous image, I said something like these two photons. So you will have to use these two photons. That also means that these two photons have to be there at the same time. They have to be at the same place, but also at the same time. So, and you can achieve this by just offering a lot of photons to your sample. But then, yeah, you create also too much heat and adverse processes. So the solution to that is to use femtosecond lasers, because then you have a very high peak power. But because the laser pulse is very short, then the power can go off again. And the average power is then still acceptable, and that the tissue stays alive and is not damaged or anything. So we need very short pulses in the order of 50 to 100 femtoseconds to do this. And that's why we need lasers. So there are now very briefly some basics about ultrafast lasers. So the basic element of a laser is that it is a cavity, Trilholte. And this cavity is formed here by these two mirrors, this one and that one. So that one is called the output coupler. This is a high reflector. And the output coupler, so both are really mirrors. This is a 100% reflective mirror. And the output coupler has a reflection of maybe 99%, so that 1% of the light is transmitted. And this is how you get your light out of this cavity. And then we have a gain medium that is pumped. And in the gain medium, we create an inversion population. And then we need some other things like mode locking and dispersion compensation. And the mode locking is what we explain here. So in this cavity, many modes can exist. So many modes of slightly different wavelengths can exist in this cavity if this condition, of course, is satisfied. But if they just randomly coexist, you don't have a femtosecond laser. What you need to do is you need to lock these modes together. That is the mode locking mechanism. Because if you do that, well, yeah, rather if you don't do that, and they have a random phase, all these different modes, and you add them up, you get noise. And so there's nothing. But if you manage to make sure that at one position or at one time point, and time is of course, yeah, so this pulse travels through between these two mirrors. So time is also place here, so you go back and forth. But if at some point in time or place, these modes have the same phase, they interfere constructively, and you get this nice short pulse out. And well, you need a lot of modes to be locked in the same place, because here we show that again, so how these different modes add up. And you see that you need a lot of modes to have this good destructive interference. And to make a very short light pulse of, let's say, 50 femtoseconds, you need a really wide wavelength, a broad spectrum. And that is actually Heisenberg uncertainty principle, because if we have this very short laser pulse, we know time very well, so delta t. And if we know delta t very well, we cannot know delta e or delta omega, the frequency with the same precision. And that is translated here, and that you have this very wide spectrum. We don't know the exact frequency anymore. Yeah. Okay, So that about, nou ja, that was a very short, the basics of laser, femtosecond laser pulses and why we need these laser pulses. Are there questions about that? So feel free to raise your hand if any unclear. Because now we go on with the contrast mechanisms. And there are several, but I'm not going to discuss all because, for example, Raman microscopy is also a non-linear microscopy, but it's covered, I think, by Freek Arissen. And we are going to talk about in the rest of this lecture about third harmonic generation, second harmonic generation, and 2 or 3 photon excited autofluorescence. And in third harmonic generation, you have 3 photons which are incident on the sample, and then the sample, the tissue, converts these 3 photons into 1 photon with 3 times the energy. And this, in the second harmonic process, this the same thing happens. There you have 2 photons which are converted into 1 photon with 3 times the energy. And before I talked basically about this process, that you really have absorption here. And now this can be absorption by a dye, by extrinsic chromophore, but also, like I said, there's blood, so hemoglobin and fat absorb light, so they're intrinsic chromophores. And here you see examples of NADH in the cytoplasm of the cell, and elastin are intrinsic molecules which absorb light, and if you excite them, then they also emit fluorescence. But then you make a real excited state, and you note it here now by this gray bar. But these 2 processes are virtual, where you make a virtual excited state. And it means that you do not make a real excited state, so the light is not absorbed. It's just that the oscillating dipoles in your sample, they start to oscillate either linearly with the impingent electromagnetic field, or they, because it's a very intense field, you have some deviations, some non-linearities, so they start to oscillate with 2 or 3 times the frequency. But that's one other big advantage, is that you don't absorb light, so you don't really heat up your sample. At least, yeah, you don't rely on that. So I will, in a moment, I will talk more about the mechanism behind this. This is just a figure to show you again the energy level diagrams, like I had in the previous slide. They would translate into a spectral representation like here. And suppose we start here with a 1200 nanometer laser beam, and the second harmonic is at 600 and the third harmonic at 400. Yep. Now that here the scattered light, the frequency of the scattered light. So so here it's exactly 2 or 3 times the frequency of the incident light, and in Raman, so in Raman you always end up in a virtual vibrational excited state, right? So this may be also not really absorption, but you have some scattering of 2 beams. And so your pump and your Stokes beam, for example. And then yeah, this if this energy difference between these 2 laser beams match the vibrational spectrum of your system, this happens. And that is how you get information about, yeah, where exactly are these vibrational levels. So that's what you do with Raman. But here we just look at really at the second or third order, the higher harmonic generation. But if we shine this intense laser light on the sample, there is always also, I suppose, I'm now explaining the cars and the microscopy, the coherent Raman processes. But there's also, of course, a spontaneous Raman scattering process going on here, there, but we just don't bother to detect those signals. But we could. And if we would add another laser with slightly different wavelength, yeah, then we would have a Raman signal. And the reason, you may say, why? Well, why don't you do that? It would be nice, but I really want to make this translation to the clinic, like we have been doing. And for that, so yeah, at some point you have to make some decisions, and I wanted it to be simple. And to have these two laser beams, that means that you need two lasers focused on the same spot. Also, in time, they have to overlap. So it's more expensive because you need two lasers. It's more difficult to align. This is just simple. Anyone can do it, right, Sophie? Yeah. So this is that, and that is why, and also these signals are a lot weaker than those signals, which is also important. But you don't get this vibrational fingerprint. So yeah, it's a matter of you have to ask yourself, what do you want to do, and what is important, and then you select your experimental methods. Okay, but this is so basically this. So I want to explain, because this is how you relates to the next slide. So if I have a laser at 1200 nanometer, then I know that my second harmonic is at 600 and my third at 400. And so if I put, if I have a detector and I put a narrow band filter which only transmits 400 nanometer light or only 600 nanometer light, then I know which signal I detect. Yeah? And if I want to look at these 2 or 3 photon excited processes, I put a filter which transmits this wavelength range in front of my detector. And this is indeed what we do here. So this is a setup schedule of a scheme of the setup. So we have here the laser. We have the acoustic modulator that Sophie can explain in a minute what it does. We have here the Galvo mirrors to scan in the X direction and the Y direction to make this 2D image. We have here a scan lens to blow up the diameter of the beam so that we can later fill this objective and focus to an even tight, very tight spot. And then here, and then these signals, so I didn't say that, but if I do this second harmonic process, for example, so I have these 2 1200 nanometer photons which transform into 1 photon with 2 times the energy, I have the law of energy conservation, right? But there's also something like momentum conservation. So in fact, all these signals are generated in the forward direction, like also shown here in this image. So what I should do is have my detector here. These signals are generated in the forward direction. They have the same impulse, the same direction, K vector, as the incident laser beam. But on one hand, in the end, I want to make a probe which I can point at the brain, and then I need to detect. And if I need to put my detector here, there's not this light, the signal is not coming through the brain, right? So I need to detect in the backscatter direction, and also like we do now with these ex vivo samples, it's easier to detect in the backscatter direction. And that is now possible because we use this long wavelength light, right? This red light that scatters not so much, so it can penetrate deep into the tissue. And then the blue light, which is the second harmonic or the third harmonic, that has a much higher scattering coefficient. So that scatters a lot. And it scatters so much that we can put a detector here in this backscatter direction. So we have here a dichroic mirror that transmits red light, but it reflects blue light. And in this way, we have enough signal to generate an image. And so here we split off these signals using different dichroic mirrors. And like I said, these filters to select the 3 individual signals that we want to detect. Now, Sophie, do you remember where we used the AOM for?
Not really.
It is, let me first talk about this. So what we expect here. So in fact, we started with a 1200 nanometer laser, but we really wanted to make this translation to the clinic. And this 1200 nanometer laser was big optical table, very expensive. So then on the market appeared fiber lasers, which are really small, like this. And they're also a lot cheaper, but they operate at this a little bit more blue wavelength, 1050 nanometers. So we were worried that the third harmonic, which is then around 350 nanometers, would not pass through our objective lenses, but then at the same time also UV transparent objectives appeared on the market. So we were really lucky. So we can work at this wavelength range. And then we get a resolution of 0.4 by 0.4 micrometer in X and Y. And then in the Z direction, it's a bit worse, so 2 micrometers. And we can image very fast, also larger areas. And we have a low power on the sample. And to achieve that, we needed this acousto-optic modulator. Because like I said, so these femtosecond pulses, we need to have this peak power. But then if you calculate, so we do pixel by pixel scanning. So we scan this GALVO, and then we are at a certain position, and then in this position, we need to measure one signal, 1 pixel. And we need at least 1 laser pulse per pixel, right, to generate the signal. But if you take a minimum of, let's say, 5, and then you can calculate that you need a laser with a repetition rate. So the repetition rate is how, when your next laser pulse comes. So this. So this pulse is let's say 50 femtoseconds. 10 is 10 to the minus 15 seconds. This is very intense, but the average power is determined by how what the ratio is between this and how long it is off, right? And you want to scan, you want to achieve a certain frame rate. So you can calculate that if you have a repetition rate of between 1 and 10 megahertz, this is optimal. And this acousto-optic modulator is there because we start with a repetition rate of 80 megahertz. This is just given by the laser that you buy, and it varied with every laser that we had. But then with this AOM, it's actually it gives bursts. So this is like this. Oh, this is also short. And this AOM then says, okay, but now closed, and here I'm open, and I give you these 5 laser pulses, and then I'm closed again. So in that way, we can play with the bursts, bunches of laser pulses on the sample. And have the average power really low, because 5 milliwatts is like a laser pointer. It's really low. Like I said there, so last week I gave images to this person who wanted to present this at the conference of the laser company. And he couldn't believe that we really use 5 milliwatts only. 100 milliwatts is much more common. And that is just by playing a bit with this, no, not playing a bit, but by reducing the repetition rate with this AOM. Yeah, clear? More or less? Okay, then now I said second harmonic, said third harmonic. So what is it now exactly? And what because the simplest explanation is like I gave you, right? You have 2 photons and the tissue transforms that into 1 photon with 2 times the energy. And another way of looking at it is what you see here. So if you would have material with a harmonic oscillator, this is a potential energy surface. And if this is an unharmonic potential energy surface, and if this would be harmonic, there would be no signal. Because what you see here is the driving optical field in the blue arrow. So it's basically here, this electromagnetic field. And it drives now this electron in this potential energy surface. And because it's enharmonic, you get something out which is always on. So it's because the electron distribution is always displaced. That is the always on part, the red arrow. And that's the process of optical rectification. So this displaced electron distribution goes on if your laser pulse is on and off when the laser pulse is off. But you also have the green arrow, which goes with 2 times the frequency. And so you should really see this as that the way light propagates through materials is that you have the electromagnetic wave, and then in the air, not the table because it's not very transparent, but in liquids and in anything where light travels through, the polarization. So all the electron distributions start to oscillate in phase with this electromagnetic field. And sometimes when this response is very, when the electric field is very strong, you get these non-linear responses. And then you get that it not oscillates in phase with the electromagnetic field, but with 2 times the frequency. And for example, so for the third harmonic process, you can think of, for example, lipids. So lipids, they have this single bond, double bond alternating structure. And you've learned, right, that this means that these electrons are delocated over this whole backbone chain. That means that these electrons, they can travel. And when you have the electromagnetic field incident on these lipids, they will do this, like I just said, they will oscillate in phase. But if the electromagnetic field is very strong, there will be a nonlinear component to this. Now, if you do the calculations for second harmonic generation, you will find that you need a sensor-somatic structure for this process to occur. And it means that it is sensitive to non-sensor-somatic molecules like collagen, and it has this handedness. I will show you on the next page, but also surfaces where you go from one to the other. Here, collagen is made up of proteins, and we have these different sort of chains, and they fold up in this pro-collagen structure and into fibrils and finally into fibers, but they have this handedness in their structure. And that's why they produce very efficiently a second harmonic signal. And for us, that is very fortunate because there's a lot of collagen in your body. So it's important to image that. And for third harmonic generation, I could have used the same formalism. And I don't want you to remember all this. I just want you to see here that we have, I didn't say that in the previous slide, but you have here the molecular parameter chi3, so the third order nonlinear susceptibility. So for the second harmonic generation, we had the chi2, second order nonlinear susceptibility. It is the molecular parameter which says something about these lipids, whether how loose these electrons are and how they can oscillate in third or respond in third order to this incident electrical field. Here you have the intensity of the incident electric field to the power 3, because that is basically the translation. If you have 3 photons, and the signal depends on these 3 photons together, so it's the intensity to the power 3. And here you have a phase vector, and that's the GUI phase. And if you calculate, and so here you have your electromagnetic field, it's focused with this lens. And if you now have here this medium with a high chi3, so you would say, okay, a lot of third harmonic generation, then it turns out that the signal generated slightly after the focus and slightly before the focus, they have the opposite phase. So you have destructive interference and you have no THE. So what you need is a discontinuity, a material which suddenly has a higher chi3 than the environment, and then you get a net field emitted from your sample. So that means that the third harmonic generation is sensitive to all kinds of optical interfaces. So either, really like you see here, you go from one interface to the other, where the chi3 is very different, or where you have a granular material which with alternating chi3 properties. Now, and it turns out that this is one of the first images we collected, that the brain is, the brain is full of lipids, right? In the, like the myelin around the axons and so on. And these lipids, they have a high chi3. And so the brain really very efficiently generates a third harmonic signal. And because, these dendrites and axons, they are inhomogeneities on the scale size of the focus. And you also see here these black shadows. And these are the cell somatas, which apparently are too homogeneous in this example to generate any signal. I think it's about time for a small break, but maybe there are first some questions about this part. No? Okay, so shall we take do you want the full 15 minutes or 8 minutes? No, 8 is fine. Shall we do 8? And we come back here at 14:30. Okay. Zijn er inmiddels weer vragen opgeborreld? Nee? Oké. Nou, dus dit was even de eerste plaatjes. Hier scannen we door zo'n plakje muizenhersenen helemaal heen. Oh, sorry. So this is a scan through through a full slice of mouse brain. And And the scan depth is here 360 micrometers. And it may sound not so very deep, but for an optical technique, it is quite deep. Nou ja, we showed that you can image various brain structures. So here the gray matter. Here you see the corpus callosum, so the bundle of axons which connects the left and brain hemisphere, the left and right hemispheres of the brain. And like I also saw in the movie, but I was very briefly here, for example, you see blood cells in a blood vessel. And yeah, this is, and then we said, well, let's see what we can see for the brain tumors. Yeah? So that was our motivation to start this work. And here again, yeah, how these brain tumors may look like on MRI images. So there's only a minority is really a solid tumor with a well-defined boundary. Most of them have this diffuse growth pattern. And so what we need is to be able to detect in backscatter direction, because we want to be fast. And that's also where we want no tissue preparation. So what you will see is that we have the tissue, we just put it in a little tray and put the tray in a microscope and image. And the first measurements that I showed you, so they took longer because we needed to learn and optimize. But now, in the end of the talk, I will also show you some studies that we did in the endoscopy suite of the lung department, and where we gave feedback to the surgeon within 5 minutes, 7 minutes. And that's why here already the focus on fast and no tissue preparation. Well, we need this resolution on a micrometer scale, but we want to have a large field of view, and we say here millimeters, but in the meantime, we have now centimeters. And we need to compare this with the histopathology, because that is the golden standard now. So these studies all look like this, right? So this was my postdoc at the time, Nicolai Koesman. We picked up brain tissue in the surgery. Then we did our imaging with it, and then the tissue went back to the pathology lab for the normal procedure, so the H&E staining, so that we could have the two methods next to each other and compare the images for quality and information for the whole validation process. And this is an image here. The blue one is the Blüher staining, where it's stained for the axons. So you see here the transition from the white matter to the gray matter. And in every area of the brain, because this is a piece of 5 millimeter, you see structures which are typical for that area. So here these neurons and other cells, here the blood vessel. And here you see the third harmonic image. And I have to say, I didn't say that, I think, but we give all our third harmonic signals, we give the color green, and our second harmonic signals, we give the color red. And that is, of course, completely arbitrary, but that's the way we do it. And here, so here you see it's very green. So we have a lot of THC signal, and there it becomes a bit less, and you see, yeah, some scattered red signals in between. So we also have here this transition, and we can also zoom in and see every cellular structures in there. And yeah, you don't see that in the back, but we can. You see here the cell, but also the cell nucleus very nicely for each near the brighter. For each of these different cells, you can also see the nucleus. The big difference is that this takes 16 hours to process, and to make this image at that time took 5 minutes, and now we're even faster. So that is a big difference, and it opens up the possibility for intraoperative feedback. But for that, you also need to be able to distinguish, of course, healthy and tumor tissue. So this is an image of a patient which before the surgery had the diagnosis of a low-grade glioma. And in the H&E staining, so there the H&E stains the DNA, so you visualize the cell nuclei. You see that here the density of nuclear density of cells is larger than there. And this is actually too large for this area of the brain. So from that argument, you say, okay, this is tumor tissue because there's just too many cells. And if we look at our image, we see also a kind of transition. So there it's very green. Here you get more black holes. And if you zoom in, and you see that in this area, you see a lot of this neuropil, this carpet of axons and dendrites that give a lot of green signal, and an occasional cell. So you see the cytoplasm and the nucleus. But in this area, this whole carpet of axons and dendrites has almost completely disappeared. You see only a few cables are left. And this whole volume is now full of cells, of which you see here the nuclei. So with the same arguments as here, you can say, okay, there are here so many cells. These must be tumor cells. And again, the time difference is notable. But the pathologist also looks at the cell morphology. So for example, the ratio between the cytoplasm and the nucleus is important. So here you see two matching sets, and here two matching sets with a very large cytoplasm and a smaller nucleus. The shape of the nuclei, so here it's not round, but see here that all the nuclei have a elliptical shape, and it means it's a high-grade aggressive tumor. And in the vicinity of the tumor, you see other differences, which I forgot the name here. And you can also see the increased vascularization associated with the tumor. So that was a nice first result. And then we went on and we imaged more kinds of tumors. And you see that for every type of tumor, so oligodendrogliomas, astrocytomas, or glioblastomas, we see a different, the images look different, but every time there's a good agreement with the histology overall. And for the pathologist, it is possible to look at these images and make the diagnosis of what kind of tumor it is. But we also, at the same time, we thought, well, it's nice, but can we make this more quantitative? And we worked on automated image analysis processes, and this started in 2016, I think. So we started with a classical algorithm, where we this was a PhD student who started out as he was trained as a mathematician, so he had no problem handling these kinds of things. But in the end, what he did was, and so you see these images, so they are either the signal is either not there, so it's black, or it's intermediate in intensity, or it's very intense. And what he so it's what you call a three-phase problem, and he used that to segment the cells. So by this black area, so the cells, we count the cells now, to segment the neuropil. Brain cell density, nucleus density, neuropil density. And then you can count that for the different types of tissue. So we had normal tissue. You think, where do we get normal brain tissue from? Well, that's from epilepsy surgery. And so they try to remove then an epileptic focus. And in the process, they also take out healthy tissue. And low-grade and high-grade tumor tissue. And you see that for every case, there's, if you quantify these segmented features, there's a very good separation. So all in all, if you translate that into a map, so here's the map, the individual counted features, you combine that and you say healthy or tumor. And then we had that because of the three pathologists look at all these images and you see that there's very good correlation, good overlap. also for other maps. And in the end, there was a 93% agreement with the pathologist. And now we also work on this correlation with MRI. We also use now artificial intelligence, so neural networks to do this automatic image analysis, because this algorithm was really good, but it's very slow. And because we have this real-time imaging, we also want a very fast image analysis. So this was actually so promising that we also started a company to, this was all done on my big lab setup in Laser Lab. And what I said there was, we should be able to make this into a nice, small, compact device that you can just put on a cart and roll into the surgery room. And we should be able to do this on the tip of a needle. And okay, I should stop here and go to the other. I stop my share here and I go to a different presentation. So this one can go. And then share screen. Okay, so I continue here with some newer work, different presentation. This, by the way, so I showed you that we went through this mouse brain slice, right, from the top to the bottom. This is now what we now, a few years later, through a human brain tissue slice. And it starts at a very red-green signal. So, and this is in the context of a project that we do investigating a hypothesis underlying multiple sclerosis. I'm waiting for the start of the movie, but there are so many, it takes a bit long time. Yeah, so here it starts. So this is the dura, so this is around the brain, and here you're now in the gray matter, and different area of the brain. You think, oh, it gets pretty dark. But now you go into the white matter with all these axons and neurons. And what they're interested in this project is to measure these swellings that you see here in these axons as a function of things that may trigger this. Anyway, I think it's nice. Oh yeah, now maybe this then. So in the meantime, so this expanded because we have now these mobile setups, 2 of them, and we imaged on brain. I showed you some results on that, but also on all these tissues over there. And it's important. So clinicians are interested in this to see whether, if they do a surgery, whether the margins are free of tumor cells, to do a very quick diagnosis so they can start treatment earlier. And they can also talk to the patients immediately about the result of a surgery and not, let's say, a few days later. And also biopsies. So now I'm going to talk more about our lung biopsy project. So if they have a patient with an uncertain diagnosis, they need to know what it is, and they really need to take some piece of tissue of this suspected area. And so they go in with this bronchoscope and a little aperture, or freezing. They actually sometimes they freeze the tissue and then, but they tear it out. So with every biopsy they take, there's a risk of bleeding. And there's really a mortality for this procedure of 1%. And they wouldn't do this, of course, if it wasn't necessary. But on the other hand, so they now take these biopsies blindly. And they take then, let's 6 on average, just to increase the chance that they have not healthy tissue, surrounding tissue, but from the suspect area. So, and with our technique, we investigated whether we could reduce the number of biopsies, because if you quickly look at the tissue, you can say, oh yeah, it's representative, and this is the diagnosis, and you can stop taking a biopsy. Yeah, so this is the machine, like I ended my previous presentation, like I want this machine. This is what it looks now. So this is card number 2. That is now in the Princess Maxima Center. So it's a pediatric oncology hospital. And the other one is here in the Amsterdam UMC, where we do this, still also do studies. Yeah, so now I pick it up. So this is one of my PhD students. She's almost finished, Laura. And she has now a little piece of tissue, puts it in the microscope. And then immediately when she closes, this is a little camera that we have on top of the setup. Now she opens the shutter of the laser and immediately there's an image. And well, she can navigate through all these, and you see that this is really live imaging, right? So it's video rate. You see the full image here. And we have to realize that all the time here, this laser is scanning very quickly over this 2D image, but it's so fast that you don't see this. And then there's also the setup that Sophie measured on. It's a lab setup. It doesn't look as fancy as this, but it's more open. So it's more accessible to change things and more like a research setup. Okay. So this we did for the lung. Again, so we have these 3 signals, and now you see in this example, you see a very clear blue signal. This is this autofluorescence signal, this 2 or 3 photon excited fluorescence. In this example, this comes from elastin. So this is an artery, and you see that the inner wall of this artery is composed of this elastin to make it an elastic structure. That's funny. Of course, I'm not a pathologist, I'm not a clinician. So when we get these images for the first time, it's like, oh, it's beautiful. What is it? We have no clue. But now we know what it is. So inside you see some blood cells. And you see here epithelial cells, and in red you see collagen of the outer wall of this artery. This is healthy lung tissue. So you see here an alveolar structure, alveolus, here in composed of elastin and collagen. And inside there's still some mucus in the patient, so air bubbles. And it's measured in 3D, so you can make a nice 2D, 3D rendering. And this is the comparison with the histology. That's healthy tissue. This is tumor tissue. Immediately you see this because it's green. There are a lot of cells. So that is very obviously different from the previous images. And the pathologist can recognize from how the cell nuclei look like and the growth pattern. So this is a very particular growth pattern. What kind of tumors these are. So and well, so one of Laura's project really consisted of just imaging a lot of these biopsies of these patients, and then having the pathologist look at all these images and make a diagnosis based on our images and compare that with the diagnosis from the histology. And you see that to judge whether the biopsy quality was sufficient, these numbers are pretty high. But the agreement with our technique and the histopathology was 85%. And we thought, yeah, 85, why is it not 100, right? So we looked into where this went wrong. So in what cases? And here, first, where it was scored correctly by the pathologists. So this is, you see here a lot of blue, so elastin, you know now. So we don't see green. So this is no malignancy. This is only connective tissue. Again, a lot of blue and red. So this is fibrosis and elastosis. It's also no malignancy, so no cells, no tumor cells. Here you do see cells in this green area. Now you have to realize now the field of view is very a lot larger, right? So to see the individual cells, you really have to zoom in here. But these cells, they are on the border, so they're actually epithelial cells, but it is also a precursor of cancer. It's actually a metaplasia, but they score this as not malignant, and that is in agreement with the histology. Here, this is the zoom in area where you can see the individual cells. This is also a large area of cells. But I don't remember why this was not what it was. But this is malignant. So this is a mesothelioma. So this was also scored correctly. So as you can see here, really, yeah. So you see here these 3 lobed cells with 3 nuclei, very irregular aspect. So even for us as non-pathologists, it becomes a bit easy to recognize this almost. This is a carcinoid, so a very green, dense mass of cells. Non-small carcinoma also scored correctly. And this they scored incorrectly, because they said, green, green, green. So this must be malignant. And but this area, if you compare that to the histology, you don't see any cells here. What this is actually necrosis. So this is where the inside of a tumor, really all the cells, they are destroyed. So you have cell fragments there and a mess, a soup. And that is also what you see, right? So if you zoom into our images, you see no cells. It's just a soup of fragments of remains of these cells. So this was not a matter of our technique not being right, but of the pathologist not being trained sufficiently. And fibrin, so this was also this, they said, oh, green must be tumor cells. But if you zoom in, it is fibrin. So it's a deposit of protein structures. It's not cells, but it's a fibrous mesh. So I can go on like this a little bit. But for us, this was interesting because so this was this next phase in this whole project. Bring this into the clinic, have it scored by pathologists, and then you have these pros. So how well do you train the pathologist if this is the data set you have, right? So that's also something to learn for us. And now one more example, then I stop, is, and just because I like these images a lot, it's the thyroid project. So the thyroid is here, right? It's up in your neck. It says shaped like a butterfly. And so relatively a lot of people have a nodule in that, but only a minority really has cancer. And what they do if they suspect cancer is they take out half of this thyroid. And then in 30% of the cases, it turns out that is really a malignant tumor, and that then they should also take out the other half. But then the patient has to come back for a surgery, for a second surgery, I mean. And actually the surgeons, they approach us now, so it's nice we're now in that phase, to see whether our technique would be intraoperatively good feedback on whether it's malignant or not. So this is a really huge image, 1.6 by 2 centimeters. So this took 15 minutes, 15 or 20 minutes, so a bit longer. And what you see here, I'm going to go to the next one, is a this green thing up there is the nodule, and I think we zoom in more, so we see more, and then you see here the follicles, the thyroid follicles, which are filled with this thyroid globin, and this now shows blue fluorescence, really interesting. And then here we go, this is the capsule of the collagen, and here we go into the healthy structure, and you see the different cells, and then you see, and you also see the follicular structure is a bit different. Yeah, so I was happy with this. I like this a lot, but it's always more beautiful, by the way, on my laptop than here. But so this is in the stage where we now are preparing a publication, because we see healthy thyroid, we see tumor thyroid, but we have not answered really yet the clinical question, can it help? And that will be the topic of a further study. Okay, yeah, I'm going to skip this. This is a nice, because we're now also in this pathology lab on the Princess Maxima Center. Deep learning. So suppose you're interested in your for your internship to do some deep learning projects. We have now a lot of data, so we are developing also deep learning algorithms, and we have now an expert on that also in our own group, so that's really nice. And yeah, so this is the conclusion. So because we made this selection for a relatively simple technique, not a Raman, but something simpler, which can still give a lot of information, but then really fast, I think we can really help out at certain points in the clinical care by giving very fast feedback on the sample quality of biopsies or on surgical tissues. And maybe even we can accelerate the pathology workflow. Actually, I also didn't talk about this, but already in 2016, we showed that you can indeed image through a needle. But we need to do that better. It's already a few years ago, so now we should be able to do better before we bring that into the hospital. And yeah. So that is the outlook. Yeah. Right. Okay. Thanks. And I should also thank everyone. This is a not complete list because the collaborators keep on growing. Of all the people who contributed to this work. And thank you for your attention. Are there any questions?
That tissue, let's say, or is that something that should have been created not to be
Yeah, no, it was classified as tumor tissue, and it's not tumor tissue. Yeah. So that was really a misqualification, and it's just that yeah, that is basically the problem with third harmonic microscopy, that it generates a signal on all interfaces. So you really have to look really what is it, or have the help of the second harmonic or the fluorescence to give more context. But in any case, in this case, it was really an example of that the pathologist had never seen a THG image of fibrin, so they didn't know. Yeah. Yeah. No other questions? Okay, well, thanks. And if something pops up, you can always email me. And I will try to answer. And also no questions in the chat.